PC SJBIT. Today we will be discussing about the module 2 memory system and basic processing unit in the subject named COARM, which is for 5th semester 21 AC 52. Under this subject, according to VTU, it has two parts. The first part is covering about the memory system, and the second part is covering about the basic processing units. And in the memory system, we have different memories. In detail study about each and every memory, like semiconductor RAM, ROM, speed, size, and the cost, as well as the cache memory, mapping functions, and replacement algorithm. And in basic processing unit, we'll be looking at the fundamental concepts and executing a simple complete instruction and multiple bus organization techniques. In that, again in hardware controlled and microprogram controlled concepts, and apart from that, basic concepts of pipelining. So this is the textbook which we will be following, which is Karl Hammacher 5th edition, which is available in the library. So in the first part we'll be covering these concepts, like basic concepts of the memory, then followed by semiconductor RAM memories, SRAM, then read-only memory, comparison with respect to speed, size, and cost, as well as the cache memory, in that mapping functions and replacement algorithm, then followed by the performance consideration. Coming to the basic concepts, the maximum size of the memory usually can be used in any computer. It can be determined by the addressing scheme. So here you can observe the basic functioning of a memory to the processor, connection of the memory to the processor. So in the processor, as we have seen in module 1, we have two registers allocated for memory interaction. One is MAR and MDR. MAR indicating memory address register, which can be used to hold the address of the memory to which memory location you are interacting. The address of that will be stored in MAR register. Then coming to memory data register, which is meant for transferring the data in between the processor and the memory. If I want to transfer from processor to memory, data from processor to memory or from memory to processor, it can be done through MDR, memory data register. So the memory data register can hold a data of n bit size. Usually that is of a data bus. Size of the data bus, if I consider 8-bit, means MDR usually it can store an 8-bit data. If it is a 32-bit and data bus, then it can store a 32-bit data in MDR. Apart from this address and data, you need control lines also. So to indicate about whether you are doing a read operation or a write operation into the memory, and some of the control signals like MFC, which is indicating about memory function completed. That means particular read operation or write operation which you are doing, whether it is completed or not, is indicated by the control signal called as a memory function complete, MFC. So it is meant for coordinating the data transfers. And the other control lines may be added to indicate the number of bytes which you need to transfer. All those things can be added in the control lines. So this is a basic connection diagram which shows the connection between memory and the processor. And one more important concept here you need to know is address bus. Address bus depends upon the number of address locations that you have. Suppose if I have a k bit address bus, you can access an address locations up to 2 power k. For example, if I say the k is 2, so 2 bits which you are using for allocating which you are using for addressing the memory uniquely. So 2 bits means you will get a combinations as 00, 01, 10, 11, 4 combinations. So 2 power 2. We are getting 4 combinations. Suppose if I increase that to 3 bits, So 3 bits means you can address the memory, each and every memory uniquely of up to 2 power 3, indicating 8 address locations. So starting from 0000 to 111. Likewise, suppose if I increase the k bit, the memory locations, address locations also you can increase. So if I have k bit address bus, 2 power k address lines that you can get. Whereas the data that it can store in each and every location is specified, or it depends upon the data bus. Suppose we have about a 16-bit address bus. So that means 2 power 16 address locations that it can have. Similarly, if I say that 8-bit data bus, so in each and every memory location it can store an 8-bit of data. Data bus indicating the data, amount of data that you can store it in a memory, whereas address bus indicating the number of locations that you can use for storing the data. And as you already known about this, the memory is usually it is a byte addressable, indicating each and every byte of memory, byte indicating 8-bit data. So each and every 8-bit data will be having a unique address. Suppose if I have 4 bytes indicating about 4 bytes indicating one word. Okay, so 1 byte indicating 8-bit data, 2 bytes comes around 16 bits. Similarly, if I say 4 bytes, which is 32-bit, so 32 bits that you can have in memory location to store the data. 4 bytes is used. So this is a diagram indicating about the concepts, basic concepts. Main measure of this memory, the speed of the memory depends upon majorly 2 parameters, which is memory access time and memory cycle time. So name itself indicate memory access time, the amount of time it requires to read or write the operation, that is to complete one operation, the amount of time that it takes. Similarly, to access the data, whereas cycle time indicated to complete the in one cycle the amount of data that you can transfer in between the processor and the memory. Memory access time and memory cycle time, these two are the one which is important measuring parameters for the speed. So memory cycle time, which is the minimum time delay required between the initiation of 2 successive memory operations. In between 2 successive memory operations, the amount of time required, time delay required, which is indicated as memory cycle time. Then memory read. So an important design issue is to provide the computer with as large and fast memory as possible, but that too within a given cost target. So you have to have a large memory and fast accessing, and within a less price, for a less price. So several techniques were used to increase the effective size and the speed of the memory. So basically we have 2 types of increasing the speed and the size. One is the cache memory, another one is a virtual memory. Cache memory, which is mainly meant for increasing the speed, effective speed. If I want to increase in between the processor and the main memory, we will be using a cache memory. Similarly, virtual memory, which is meant for increasing the effective size. So coming to the memory system, semiconductor RAM memories, SRAM. So here, as you already know, memory will be arranged in the form of a cell. So as I told, it can store the data in the memory. How it stores the data means, suppose if I have an 8-bit data, 8 bits, a combination of 8 bits. So those each and every bit will be stored in a memory cell. So that means each memory cell can hold a single bit of information. So these memory cells are organized in the form of an array. So one row is meant for storing one memory word. Word, already I told, it is 32-bit word. 32-bit. If it is an ARM processor, it is of 32-bit. All the cells of a row which are connected to a common line, we call that as a word line. Again, the word line is connected to the address decoder. I need to know in which address location the data has to be read or data has to be written. So the word line, which is again connected to the address decoder. So we will have a sense or write circuit which are connected to the data input output data input or output lines of the memory chip. So this is the internal organization of the memory chip. As you can observe, we have in each and every row, we have a rows and columns, and each and every cell which is meant for storing a single bit of information. Each row, if you observe, will be having 8 cells, that is starting from 0 to 7, indicating an 8-bit data that you can store in one row. So the address of that, if I specify with a word data as word address as W0, second row with a word address as W1, similarly and so on. 15, W15 here you can observe. So W0 to W15 means total 16 columns we have. So 16 columns in and 8 rows. So which is a 16 cross 8 memory organization. So this is a 16 cross 8 memory cell organization, and you can observe here 16 lines if I have word address lines. In order to address them uniquely, we need 4 address lines. So as I already told you, if I have k bits, you can get 2 power k address locations. So as here I can have 4 address lines, A0 to A3. So 2 power 4 indicating 16. So 16 address lines that you can get uniquely. Starting W0 address is 0000. If I give for A0 to A3 as 0000, it will be locating to the first column. In that first column, which bit if I want to write or read, that is decided based on the sense or write circuit. So each and every sense or write circuit is provided with 2 control signals. One is read write bar and CS. So read write bar indicating whether to read the data from the memory or to write the data into the memory is indicated by that bit. Write operation is active low, read operation is active high. And another one is chip select, indicating which chip that you are using, that means which row that you are using in this case correspondingly. So totally it is about 16 cross 8. 16 address locations I have, and in each and every location I can store an 8-bit data, B0 to B7. The data writing or reading that is controlled by sense or write circuit, and the corresponding cell is detected or determined by using chip signal, and the corresponding column will be selected through the address line, which is connected to the address decoder given with the address lines as A0 to A3. So correspondingly it will be decoded. So here you can observe the cells, memory cells, each and every cell. We have two sides, two lines, one for reading and another one for writing the data of 0 and 1. That's about a 16x8 memory organization. Similarly, if I want to increase, you can increase the address lines. Obviously you can have more size of the memory. Now coming to each and every cell present in that memory location, one can notice here you have a SRAM cell, SRAM indicating static random access memory, static random access memory. So here you can observe it can be used to store retain the data as long as the power is applied. So that's the reason why we call it as a static memories. So as long as the power is present, static RAM can store a single bit of information. This is a cell which is meant for storing a single bit of information. B and B dash indicating it can be either 0 or 1. And you have a bit lines and word line. Bit line and word line indicating in which word line and in which cell correspondingly you need to select. The cells are means static RAM cells. How it will be arranged, means how it is implemented, can be shown in this diagram. One can notice that here you have two transistors T1 and T2 which are cross connected in the form of a latch, so forming a basic flip-flop. The latch is connected to two bit lines by the two transistors, so which is T1 and T2. So basic one is two flip-flops, two inverters which they are connected, cross connected to form a latch, and it is in turn connected to bit lines through two transistors T1 and T2. So these transistors T1 and T2, they act like a switch, so on or off switch that can be either open or closed with a control line called as a word line. The word line will decide which transistor to turn on or which transistor to turn off. When the word line is at the ground level, that is at 0th level, the transistors, as the base is given with a 0 voltage, that means transistors T1 and T2 are turned off. Latch retains its original state, previous state it retains. For example, let us consider that the cell is in state 1. If logic value at point x if you observe, if it is 1 and at point y is 0, that means it's a NOT gate, no? If it is 1, x is 1, obviously the value at y is 0. This state is remained as long as the word line signal on the word line is at ground level. If the word line is at ground level, these two transistors were turned off, then the position of x and y is retained as 1 and 0. So you have two operations that you can perform, that is read operation and write operation. Coming to read operation, in order to read the state of SRAM cell, first you need to activate the word line to close the two transistors T1 and T2. If the cell is in state 1, the signal on the bit line B is high, and the signal on the bit line B dash is 0. So the opposite is true if the cell is in state 0. Based on whether the cell is in which state, the data can be read through bit lines B and B dash. Thus B and B dash are always complement to each other. So you have a sense and write circuit at the end of the bit lines to monitor the states of the bits B and B dash and set the output accordingly. So coming to read operation, word line will be connected to high first, which will close the transistors T1 and T2. The latch output whatever we have, that is positions of X and Y, which will be latched to the bits B and B dash. The corresponding bit lines will be read through sense and write circuits. Coming to the write operation, the state of the cell is set by placing the appropriate value on the bit line B and B dash. First they will set the data on B and B dash and then activate the word line, and this forces the cell into the corresponding state. The required signals on the bit lines are generated by the sense and write circuit. So you can implement the same using the CMOS cell also. This is one indicating about SRAM, static random access memory. Static RAMs are fast, but they come at a high cost. Cost of the circuit is high because their cell requires several transistors, and less expensive RAMs can be implemented if you have a simpler cells are used. However, such cells do not retain their state indefinitely for a long time. They can't retain its value, so they are called as dynamic RAMs. You need a periodic refreshment in that. So you have in static RAM, you have a problem with the static RAM, as we have seen. It's of high cost, but they are of fast static RAMs are fast, but cost is high because cells that you need for several transistors that you need to store the data. Coming to less expensive than RAMs, which can be implemented with the simple RAMs, simple cells. But problem with that is you need to they can't retain the state for indefinite period. You need to refresh the data. They are called as dynamic RAMs. Static RAMs are said to be volatile memories, indicating as long as the power is on, the contents will be there. Whenever the power is interrupted, the content in that will be lost. So static RAMs consists of circuits that are capable of retaining their state as long as the power is applied. They are volatile memory. Once if power is interrupted, it is lost. Access time of that static RAMs are in the range of few nanoseconds. However, the cost of that is usually high. That's the reason why we go for dynamic RAMs, DRAM. But the problem is they do not retain their state for indefinite period, indefinitely. Contents you need to periodically refresh the data. Contents may be refreshed while accessing them for reading. So this is a diagram of indicating a static single DRAM cell. If you observe, you will have a word line, bit line, and a single transistor along with a capacitor. So transistor turn on or off is decided based on the word line, and once if the transistor is active, the data which is present on the bit line will be charged by the capacitor. Suppose if bit line is 1, capacitor is charged to the high voltage, and it will retain, as we know that capacitor can hold data for not for a long period. Again you need to do a refreshment. Data has to be refreshed. So this is a diagram of asynchronous DRAM. which is of size 2 megabytes, 2 megabytes, 8-bit dynamic memory chip, internal organization. Here you can observe row address, column address latch, and row address lines and column address lines, sense and write circuits, column row decoder and column address decoder, likewise. So here one can notice it is it can be 16 megabit DRAM cell. It is of 2 mega cross 8, indicating 8 into 2 total 16 megabit 16 megabit dynamic RAM cell. So what they have done is they have decomposed that into 2 cross 8, 2 mega cross 8. So again the cells 2 mega that they can implement by using 4K cross 4K, which is of 8 into 2 16 again. So 4K cross 4K. So 4K again they can group it into 512 into 8. So 512 lines, 512 into 8, it comes to 4K. So total indicating 4K RAM. And again for 4K, how many bit address lines that you need means for 1K you need 10 bits, 2K you need 11 bits, for 4K you need 12 bits. So for 512, for 256 you need 8 bits, for 512 you need 9 bits. So total if I have from 0 to 20 address lines, indicating total 21 address lines, it will be divided into 9 address lines and the remaining 12 address lines. So 12 address lines for locating 4K memory, and then these 9 address lines for locating 512 cross 8. That 8 is data lines, 8 data lines. So totally they are dividing 16 megabit DRAM cell into 2 mega cross 8. That 2 mega again they can divide that into 4K cross 4K. That 4K again they can divide it into 512 cross 8 cross 4K. So that 4K cross 512 is of address, and that 8 is about the data lines. So the address which is of 4K cross 512 can be addressed as a lower address and higher address. Lower address they will divide that into rows and columns. Lower address they were dividing it as a rows, and the higher address they were using it as for columns. So in order to select the particular column or the row, you need a row address latch and column address latch, and correspondingly it will be decoded. Totally addressing about 4096, indicating 4K cross 512. 4096, in order to access you need 12 bits. 512 address bus, if address lines, if address if you want to access you need 9 bits. So that's why A0 to A8 for 512, A9 to A20 for 4096, multiplied with 8. This 8 is of data lines D0 to D7. So totally you will be accessing a cell array. So they are arranging in the form of an array. So you have rows and columns. So each row can store 512 bytes. That 12 bits will be used to select a row, 9 bits will be again used to select a particular group in a row, totally 21 bits. So first you apply a row address RAS signal which latches the row address, then applies the column address through CAS signal, latches the column address. So the timing diagram for memory unit, which is controlled by the special unit called as RAS and CAS signals. This is nothing but the asynchronous, not with respect to clock. If everything is happening with means read or write operation, if it is happening with respect to the timing diagram, with respect to the clock signal, then it is synchronous. If it is not with respect to that, then it is asynchronous. So here sense and write circuit, which will be taking care of reading or writing the data. Then you have a corresponding chip select signal, read or write bar signals. This is about asynchronous DRAMs. This is about the fast page mode. Then coming to synchronous DRAM cell. So here it is with respect to the timing diagram. So next class we will see about this synchronous DRAMs and so on. Thank you.